Today we'll review the paper survey of attacks on Ethereum smart contracts. And a small note, in the paper was written in 2017, so in the probability code that they provide in their examples might be a bit different, but we'll focus mainly on the ideas and the vulnerabilities. If at any point of the session you have some questions, just write in the chat. So the paper classifies the vulnerabilities into three different levels. So one level is liquidity level, another one is EVM level, and also the blockchain level. We'll go through all of the vulnerabilities one by one. So let's start from the solidity level and the call to the unknown. Okay, so call to the unknown. Some of the primitives used in solidity to invoke functions and to transfer Ether may have the side effect of invoking the fallback function of the calling. So basically, you saw in the lecture that if you transfer some Ether to the smart contract, you might invoke fallback function. And actually invoking the fallback function might lead to some attacks in the future. So we need to be careful when writing the code. So the first one is call. So call basically invokes the function of the contract or itself and transfers Ether to the calling. So here below in the code, you can see how you use the call. So see that call and you specify the amount that you are transferring. And in the next part, you specify the function signature. So in this case, the function is that we are calling is ping, and it accepts as an argument type uint to 56, and it takes the hash of that function and takes the first 4 bytes. So basically, when we use call, we specify the first 4 bytes of the hash of the function and pass it. And n is the actual parameter that we are passing to the function. So here we have a problem that if a function with a given signature does not exist at a thread tip, so basically it means that this function that we specified here, if it doesn't exist in the contract at a thread T, then the fallback function is executed instead. And let's go to the next slide. So here, another one is send. And send is used to transfer Ether from the running contract to some recipient as well. So the it is used as R is the recipient, and we send some amount to the recipient. And here we have another problem is that after the Ether has been transferred, then send executes the recipient's fallback. You probably have seen some examples in the lecture that when you use send and the send doesn't execute successfully, or the receive function in the contract that we're sending the amount to does not have receive function, then you would directly go to the fallback function. And the next one is the direct call. So suppose we have two contracts, contract Alice, and it has a function ping, and the contract Bob, which has a function long, and also it accepts the address of the Alice, the contract Alice, and calls the function ping 42 from this contract. So basically, contract Bob is calling the function in the contract Alice. So here we have also one problem is that if the programmer mistypes the interface of contract Alice, so basically the interface that is specified here is not correct, then then it might return a fallback. Or let's say the Alice has no function with that signature. Suppose Alice doesn't have the ping function, and it will also go to the fallback. Okay, so someone said the audio is unclear. So let me try another microphone.
So is the audio better now? Please let me know if this audio is better than the previous one. Okay, it's better. Okay, good. Okay, good. Yeah. So here we see that when we go to the fallback function, it might lead to some vulnerabilities, and we will consider some of the attacks in the next slides using those vulnerabilities. So the next vulnerability is the exception disorder. So exceptions in the smart contracts can occur due to several reasons. One of them is that the execution runs out of gas, so there's not enough gas specified, or the call stack reaches its limit, or basically the command throw is executed. So even when you write in the contracts, you write some required statements, and the required statement is not satisfied, exception also is strong. So here the problem is that Solidity is not uniform in the way it handles exceptions. So it doesn't have like one rule for handling all of the exceptions. So when writing the contract, you must be careful about this. And it really depends on how contracts call each other. And based on that, raised exceptions might have different results. Let's see an example. We have again the contract Alice with the ping function. We have the contract Bob. And here, firstly, we specify the value of x, variable x. So initially, x equals to 0. And we have another function Pong, which takes as the input contract Alice, and it sets the x value as 1. Then we call the ping function of Alice, and we set x equals true. So let's consider two different cases. So in the first case, say user invokes Bob's Pong function, and Alice ping throw an exception. So it is the way that we call the function here using c.ping. So basically, when we call the ping using the contract Alice and it throws an exception, so basically the execution stops here, and the side effects of the whole transaction are reverted. So basically everything that happened before c.ping is reverted. So and the value of x remains 0 here. So basically it reverts x equals 1 and goes to the initial state. Let's consider another situation. Let's say that Bob invokes the ping function via a call method. So basically it just says something like we've seen before. It would be c.call.value and so on. So if we use a call method, then the side effects of that invocation are reverted, and the call returns false, and the execution basically continues. So if we use the call method, then let's say that here instead of c.ping, we put c.call, and here it would return false, and the execution would continue, and x value would be set as 2. So basically, if in the first case we would have the whole transaction reverted and it would be x equals 0. In the second case, it would be x equals 2 because execution continues. So depending on how you call the contract functions, exceptions are handled differently. So you need to consider that when writing a smart contract. The next vulnerability is gasless send. So when you use the function send to transfer Ether to a contract, then you might have an out of gas exception because send is bound by 2,300 units of gas. You've seen in the lecture that the transfer and send are bounded by some amount of gas, but using directly the call method does not have the limits on the gas. So here the problem is that when you have the limited amount of gas, it allows to execute only limited set of bytecode instructions. So basically, you cannot really alter the state of the contract. And in any other case, it will end up in an out of gas exception. So every time you try to alter the state of the contract, you'll have the exception again. So let's see an example here. Let's say we have a contract C, and C has a function pay, and we send to the recipient D amount N. And let's say we have two different contracts, D1 and D2. And in D1, we have the variable count, which is initially 0. And the fallback function is that it increments the value of count. And we have another contract, D2, which has a fallback function which is empty. And let's consider the case 1. Let's say that we pass here as address D the contract D1, and in this case, the contract C would fail with an out of gas exception because in the contract D1 we are actually incrementing the value, so we are altering the state of the blockchain, and that there might not be enough gas to do so. And in contract D2, if we use contract D2, then the send would succeed because it doesn't do any state alterations. So this is about the gasless send. And another vulnerability is the typecast. So the Solidity compiler can detect some type of errors. For example, let's say you're assigning some integer value to the string variable. Then Solidity compiler might detect this, but it cannot detect some kind of like logical type errors. So again, let's consider the two contracts, Alice and Bob. And here, the problem is that compiler does not check, firstly, that C is indeed the address of the contract Alice. So basically, it might be some non-existent address, or it might be the address of some other contract, and compiler cannot check that. You need to check that manually. And the second is that the interface declared by Bob might not match with the Alice actual interface. So in these cases, you need to check all of that by yourself. So let's consider different situations. Let's say that C is not the contract address. So C is the contract address that we are passing here at this point. And in this case, the call would return without any execution of the code. And this is until the version of the Solidity 0.4. And from the version 0.4, it just throws an exception. And however, let's consider another case. So C might be the address of the contract that has a function with the same signature as Alice ping function. Then that function would be executed. So basically here, suppose that C is another contract other than Alice, and it also has the same function ping, then the ping function of that other contract would be executed. And we would not even detect this, right? Because we would think that the transaction is successful and that it didn't return any errors. And the third situation is that if C is a contract with no function matching the signature of Alice ping, then C's fallback is executed. Let's consider the next vulnerability, which is re-entrancy. So fallback mechanism may allow an attacker to re-enter the caller function. So we've seen previously that there are a lot of situations when we might enter the fallback function of the contract, and we can actually re-enter the fallback function, and it might cause some loops of invocations which would consume all of the gas. So we can actually do such attacks where we create loops of invocations, and we might even like steal all of the balance of the contract. So let's consider the following situation. So we have the contract Bob, and initially send is false, and in the ping function, if it is not sent, then we send some value to the contract C. And we also set the send variable as true here. And let's say we have another contract Mallory, which is a malicious contract, and malicious contract has a fallback function which calls the ping of the contract Bob again. So here, let's see what happens. Basically, when we call the ping function of the contract Bob, it first calls the contract C and sends some value to the contract C. And in the contract C, it calls the ping function again. So it goes to the beginning again, and then sends the answer again. And as a loop, it goes to the fallback function again and sends the answer once more. So there is a loop of invocations, and basically this way you can just drain all of the balance of the contract. And the reason why this happened is that we set the send variable as true only after the call. And to resolve this, we just need to set the variable send as true before we are actually making the call. So this is a reentrancy attack. And in the homework 3, actually many people forgot about the possibility of the reentrancy attack, and did not specify some flags such as send. So you need to be very careful about that as well. Another vulnerability is keeping secrets. So fields in the contracts, they can be public or private. Public means that it can be directly readable by everyone, and private means that it might not be readable by other users of contracts. However, when you declare the variable as private, it doesn't guarantee you secrecy. So it doesn't mean that nobody can see the value of the value that you declared as private. So because you see that when a person executes, sends some transactions and uses some private value, this transaction is actually recorded on the blockchain, so everyone can see it. They can see the input parameters of that transaction and see the values of those private variables. It just means that it can, other users cannot directly read it, but everyone can see it. So it doesn't guarantee you secrecy. And to guarantee secrecy, we should use some other cryptographic techniques such as timed commitments. So for example, even in the rock, paper, scissors game, you need to hide your value. You cannot just declare it as private, but you need to use some commit reveal schemes. And the next vulnerability is immutable bugs. Once a contract is published on the blockchain, it can no longer be altered. So the fact that you cannot really change the contract, it has been exploited in various attacks. So you might steal Ether or make it just unredeemable by any user. And there is actually no possibility of recovery in these cases. However, there was one exception. So one of the well-known attacks is the DAO attack. And in this case, there was a hard fork of the blockchain, and actually there was a recovery from this attack. But for most other contracts, it's not the case. The next vulnerability is that Ether might be lost in transfer. So when you're sending Ether, you have to specify the recipient address. However, like the contract does not check if the recipient address is valid. And these addresses can be orphan addresses, and they might not be associated with any user or contract. So in this case, you would just lose Ether because you're sending to some orphan addresses. Another vulnerability is a stack size limit. So every time your contract invokes another contract or itself, then the call stack associated with the transaction grows by 1 frame. So the call stack is bounded to 1024 frames, and when this limit is reached, then it throws an exception. However, this vulnerability was kind of resolved in October 2016. And they made it so that the call stack is always less than 1024. So probably you cannot encounter this vulnerability when you write smart contracts. And the next one is unpredictable state. So the state of the contract is determined by the values of the fields and also the balance of the contract. So when you run a specific transaction, you cannot be sure about the state of the blockchain at that moment, because when you send a transaction, it doesn't immediately alter the state. It all depends on the miners. So basically, the miners are those who decide which transactions to include and how to order transactions in a block. So everything depends on miners. So you cannot be sure about the state of the blockchain when you're actually executing the transaction. And the next one is generating randomness. So in the lectures, you've seen that generating randomness on the blockchain is a difficult problem because the execution of the EVM bytecode is deterministic, so that all miners who execute the transaction will have the same results. And let's consider 2 cases of generating randomness. So the first one is that many people generate random numbers using the hash or the timestamp of the blocks that will appear in the blockchain at a given time in the future. However, there is a problem with this because miners have some control. So basically, miners are the ones who decide on what kind of transactions to include to the block, and they might somehow adjust that to benefit from it, because they might align the transactions in the block in a way that gives you preferable hash value or the timestamps. And the second case is using time commitment protocols. So the way it works is that you have a set of participants, and each of the participants give you some uniformly run some value that is chosen uniformly at random. So at the end, you just combine all of those numbers and get a truly random number. But the problem with that is that it's not really truly random, and it requires that at least one of the participants gives you uniformly random number. So there are problems with this as well. Another vulnerability is time constraint. So a lot of applications use time constraints, and usually they're implemented using block timestamps. And the miner who creates the new block can choose actually the timestamp with a certain degree of arbitrariness. It means that the miner can, the range at which the miner can choose the block timestamp differs by around a few seconds, and miner can choose among the inside this range. And previously, in the previous versions, it was that the range was around 900 seconds, and That's why it was a huge problem that miners could manipulate the block timestamps. But now it's just a few seconds, but still it might give some advantages to the miners. So, and let's now move on to the attacks. So the first one is the DAO attack, which is maybe like the most like popular attack that is known. So DAO was actually a contract that implements a crowdfunding platform. So here we have the value of the credit. So you could donate some value to the address, to some address, and the credit of that address would increase. So basically you have the donate function and you have also the withdraw function. So when you withdraw some amounts, you first check if the credit of that person is greater than the amount. And if yes, you just send that value to the message sender and you decrease the credit amount. So this is just a simplified version of the DAO contract. And now let's see the attack. So the first attack is a loop of withdraw calls. So this is basically the reentrancy attack. We previously discussed the reentrancy attack, and we know that when we, let's say here, when we call, when we perform call and send some assets to the contract, it might go to the fallback function. And in the fallback function, we have again the withdraw function. So basically, it again goes to the beginning of the withdraw function and sends the ether again, and the loop continues this way. And the problem with that is that we decrease the value of the credit only after we send the ether. However, in this case, we should first decrease the amount and then transfer ether. And in this way, in the next loop invocations, the credit of the message sender would be probably less than the amount, and we cannot really like steal all ether from the contract. And so this one is the first attack, and the second attack is using the underflow. So let's consider another malicious contract, mallory 2, and here we have the attack function. It first donates the value of 1 way to this contract, and it then withdraws 1 way. And here, what happens? So basically, the credit value increases by 1. And then when we withdraw it, it again decreases and it goes to this call, right? And when the call is executed, it goes to the fallback function of the malicious contract. And here we do withdraw again, but we withdraw just 1 way. And we don't have a loop here. We don't have a loop here because we have this flag perform attack false. So basically, just with like 3 operations in this case, we can perform this attack. And the reason why this works is that here you see when you do withdraw 1, and initially the value was 0, right? And when you do withdraw 1, the value happens to be 2 to the power of 256 minus 1 way. Because of the underflow. And this way, the malicious contract can just withdraw all of the balance of the DAO contract in this case. So let's go to the next one. So this one is a king of the Ether Throne contract. You've seen this contract in the lectures as well. So basically, this is a game where players compete for acquiring the title of the king of the Ether. So if someone wants to be a king, then that person needs to send some Ether to the current king and a small fee to the contract. Then the king would be updated. So here we have we have the constructor, and we have the sweep commission function, where we send some value to the owner. And also here we have the fallback function, which is we calculate the compensation here and send that compensation to the current king and update the king, and also set the new price for it. So this is a simple version of the king of the Ethereum contract. And let's consider the problems here. So the first problem is that we don't really check the return code of send, and it may result in stealing Ether. So we do the send here, right? King.send compensation, and we don't really check if this send was successful or not, right? And this may lead to some problems. And send will also fail if the king's address is that of a contract with an expensive fallback. And in this case, since send doesn't propagate exceptions, compensation is kept by the contract. And now let's consider another attack. Let's consider this Mallory contract. It has a function unseat king, and it sends some W value to the king of the Ether contract. And then it has a fallback function which throws an exception. So here, let's see what happens. So malicious contract becomes the new king, okay? And then in the next time when another person or another user wants to become a king and send some value to the contract, here when we execute the king.call.value, then it goes to the fallback function of the Mallory malicious contract, and it throws an exception. And since it throws an exception, now no one can actually become the king. So, so this is another attack on this contract. And let's consider the next one, which is Pixie, I suppose. So this is a contract which implements a Ponzi scheme, which is a fraudulent high-yield investment program where participants gain money from investments made by newcomers. So the way attack was performed is that so during the development of the contract, its name was changed from dynamic pyramid to Pixie. However, programmer forgot to change the name of the constructor. So and then this function became invocable by anyone. So after this bug became public, so users started to invoke dynamic pyramid function. Since it wasn't a constructor anymore, it was just a function that can be called by anyone. So anyone could call that function and also withdraw some fees from the contract. So these all are actually like real life examples. And another contract is another situation is when we have multiplayer games. So this so let's say we have a game, odds and evens, and it's just that in this case we need to sum the values of two players and then see, let's say if it's an odd number, then let's say player player one wins, or if it's an even number, then player two wins. And in this case, when they submit a number to the game, players would assume that those values are private, because here initially we declare the players as private variables. However, as we've already seen, it doesn't really guarantee secrecy. So anyone who sees a transaction where the player calls this play number function, they can see the input parameters and they can see the number itself. And so the second malicious player might be just waiting for the first one to commit the choice and see its value, and then just do make the choice himself and then just win the game. So you need to be very careful about those private fields, because in the homework tree as well, some people implemented the hash, like finding the hash value of the choice, let's say rock, paper, and scissors, and also the nonce as a public transaction. And actually everyone could just see the input parameters. And there would be no point of having a hash function, because all of the input parameters are public in this case. But there is an exception that if you just put pure near the function, then it would be just a local function, it will not be as a public transaction in this case. So you have to be careful about all of that. And another contract is governmental. So this is another float Ponzi scheme, and to join the scheme, a participant must send a certain amount of assets to the contract. And if no one joins the scheme for 12 hours, the last participant gets all of the assets in the contract. So this is the main idea of the contract. And here we can perform several types of attacks. So let's say that the attacker is a miner who also impersonates a player. So we discussed that the miner has a lot of control. So being a miner, she can choose not to include in the blocks the transactions directed to governmental, except for her own. And this way, the miner can be the last player in the round and win the game, and get the reward. Or also the miner can reorder the transaction so that her one will appear first. Or again, the miner can play with the block timestamp. And if the miner sets the new block, the timestamp of the new block, so that it is at least 1 minute later at the timestamp of the current block, then again, she would win. So yeah, that is another attack.